Greetings, ladies and gentlemen. Welcome to video number 2 on theoretical and experimental probability. This one going to experimental, so you had to go back to page 414 to take a few notes. And ladies and gentlemen, once again, I find that the book is extremely inadequate in defining experimental probability. Experimental probability is probability based on frequencies obtained by conducting an experiment. So you actually have to do something. You know, like flip a coin. You have to actually flip it a bunch of times and do an experiment. You have to roll the dice a bunch of times. You have to pull cards from a deck. You have to do something to conduct an experiment. Okay? It could be surveys. Whatever it is, you're conducting some experiment. You're keeping some frequencies. You're making tally marks and then saying, wow, how many chose what I thought they would based on how many people I asked or how many times I rolled the die. All right? So that probability is the number of times the event occurs. Well, the number of times event occurs is how frequent it occurs, right? And that's divided by the total number of trials. How many times did I roll 4, that's frequencies of the 4, versus how many times I rolled the die, 20 times, right? All right, so here's an example. If your team won 9 games out of a total of 12, the frequency, the number of times the event occurred is 9. And then relative frequency, right out of our essential question, relative frequency is 9 out of 12. That's the same as experimental probability. The number of times the event occurred, 9. How many games did we play? 12. Experimental probability, relative frequency, basically the same thing. Let's move right along. We have to know that all relative frequencies, all experimental probabilities add up to 1. So in other words, if I asked a bunch of people how they got to work, and I got these answers right here, those are the frequencies. I then turn them into relative frequencies by putting them all out of 92. When I then add them all up, I better get 1. Now notice, sometimes it will depend on how we round the number. But otherwise, if we'd rounded it perfectly or just added the perfect numbers, it would equal exactly 1. So let's do some on our own. The bar graph shows the results of rolling a number cube 50 times. Find the experimental probability of rolling a 6. So this graph says, hey, here's how many times the number of frequencies I rolled a 1, a 2, a 3, a 4, a 5, and a 6. So I come over here to a 6 and I see that I go across and I rolled a 6 times out of the 50. And if I simplify that, I get 3 out of 25. Now if I told you the probability of rolling a 6 was 3 out of 25, you'd probably look at me because you'd be confused. Because we don't usually talk probability, especially experimental probability, as a fraction or a ratio. We usually talk about in percent. So if you turn that to a percent, and that's 12%, and I said, hey, you have a 12% chance of rolling a 6, you'd probably understand that a little bit better. Going on to number 8, find the experimental probability of rolling a 2. I come over to the 2 and go across, and that is 4 out of 50, which is 2 out of 25, which is 8%. Find the experimental probability of rolling a 4 or a 5. This or, a very key important word. It means we're going to add. So we come over here and we say, how many times did I roll a 4? Ooh, that's 11. 11 out of 50. Plus, how many times did we use roll a 5? That's again 11 out of 50. So that's 22 out of 50, which simplifies out of 11 out of 25, which again, I don't understand that very well. I can see it's just less than half, but it's actually 44%. If I told you 44% chance of rolling either one of those numbers, you'd go, oh, okay, that makes sense to me. Number 10, find the experimental probability of rolling an even number. So now again, we want even numbers. So guess what we're going to do? We're going to add, because that's like saying a 2 or a 4 or a 6. So we're going to add. And I'm going to put them all out of 50. And this time I'm going to add them on the top. So I have 4 and 11 and 6. And that's 19 out of 50. Which again is difficult to understand, but if you turn it into a percent, you would say it's 38%. Now, is that the fundamental probability? No, we know the fundamental, Is that the theoretical probability? We know the theoretical probability for rolling any number on a number cube is 1 out of 6. So these probabilities change based on experiments, but that's still not theoretical. All right. Of the 2,500 customers yesterday, 45 spent more than $100. What is the probability the next customer will spend more than $100? I bet you know that businesses use this basic math as a way of helping them understand how their business is gaining money. All right? So when we write this down, 45 out of 2,500. All right? This is the number of frequencies, 45 people out of the number of people that came in. That's 2,500. And when you simplify that out, that's 9 over 500, which is basically 1.8% of the people spent more than $100. That's what they can expect tomorrow if they use it as something to predict. Yesterday, Mr. Ross selected 15 students to answer various questions for the class. If your name was selected 3 times, what is the experimental probability of being selected again today? So we have to use, there is your name, it was selected 3 times, that's the frequency. Out of the total number of times I selected a name, 15, which is 1 out of 5 or 20%. If your name was not selected, what is the experimental probability of being selected today? Well, that is 0. You wasn't selected at all. So 0 out of 15, that's a 0% chance, which is impossible. And you and I both know it's not impossible. Your name is in there. So theoretically, your name there is a chance. And let's find out what that is. If there's 25 student names, what is the theoretical probability your name will be selected? Well, that's 1 out of 25, which written as a percent, that's a 4% chance. So experimentally, you're not ever going to get selected, but theoretically, you certainly would. All right, use it to make a prediction. A survey of 200 people found 32 had a bird as their first pet, 56 had a cat, 66 had a dog, 19 a rabbit, 27 had something else. What is the probability that a person says his or her first pet was a cat? By the way, I'm not a cat lover. I do like cats, but I'm not a cat lover. I'm a dog lover. You see my lovely dog. Anyhow, so 56 had cats out of the 200 people surveyed, and you can simplify that right on down. 56 out of 200 simplifies all the way down to 7 out of 25, which is 28%. Now it says, out of the 500 people, how many would you expect to say that a cat was his or her first pet? So that's how we're predicting. So you can use either one of these. I can say 7 out of 25 is equal to how many out of 500? And when I use cross products, it's 25x equals 3,500, and then divide by 25. Oops, I didn't put a 5 in there. I would see that it's 140. Or, if I broke it into a percent, I would say 500 times 28%, which is 0.28, I would still get 140. All right? So both ways you can use both parts of either way you write your probability. 17, a random inspection of phones coming off an assembly line found that 3 out of every 200 phones inspected were defective. If the company assembles 35,000 phones a week, how many can they expect to be defective? You think it's important for them to understand that not every single phone that they put together is going to be perfect, that they're going to have to replace some, that's going to cost them money, so they got to build that into their cost. All right? So this kind of probability is very important in business. And so that's 3 out of the 200. Well, that would be how many out of 35,000? That's 200x. And that equals 105,000, excuse me. And when I divide by 200, I would find that I could expect, or the company could expect 505, well, I'm having a hard time speaking today, 525 defective phones. So that's very important for them to know this math. It's very helpful for them to make those predictions in their cost analysis. All right. Our last 2 examples for the day. I know it's running long, so I'm going to be speaking quickly. Here we go. Heads was the winning coin toss in 9 out of the first 15 Super Bowl games played. Based on the results, how many Super Bowls can expect heads to be the winning coin toss? So you would think that over history, they would still want to select heads because 9 out of the first 15 were heads. So 9 out of 15, that means 3 out of 5. 3 out of 5 can expect to have heads. That's better than 50%. Whoa. That's better than 50% chance. Yeah, that's good. How does this compare to the theoretical probability? Well, we know theoretically it's 1 out of, wow, I'm really messing up. 1 out of 2. Theoretically, it's 1 out of 2, which is an exact 50% chance. So, wow, experimentally, you'd think people would change their mind and go with heads every time. It just so happens that out of the 50 Super Bowls that have been played, 26 of them, 26 have won tails. 24 have won heads. So that means there's been a big change in which one has won over the past 35 Super Bowls. All right, ladies and gentlemen, we're done. 21 out of the first 25 people going to the movies ordered popcorn. How many popcorns can the theater expect to sell if 3,000 people go to the movies on Saturday? Figure that out. Make sure you write down questions. Come to class with questions on experimental and theoretical probability. Finish off your 45 minutes with a quality effort, aggressiveness, urgency, using time effectively, all those things that make you who you want to be and the results that you want to have. Ladies and gentlemen, I'll see you.